What we do is risk analysis using probability and the analysis of systems. And we have done all kinds of things in seismic risk, in asteroids, believe it or not, and now cybersecurity. And it took me to interesting places. I was working on space systems, I was working in operating rooms, and I was part of the commission that looked at the BP accident. So, a few basics of our work. We quantify the risk. We separate the risk assessment from the judgments, value judgments. What I want is facts, ma'am, just facts. And we separate the risk assessment also from the perceptions, because it's very easy to whip up hysteria. And so we try to provide the best information we can to decision makers and hope for the best. So, cyber risk analysis. It's an alternative to hand-wringing, the stuff happens philosophy and blind spending of money. And we try to allocate the resources to the worst cases, because securing everything is not really feasible and it's most likely inefficient. It's like spreading the peanut butter. So we have two questions that I'm going to show you today. I have 4 doctoral students working on this topic, and I will present 2 of their theses. First, the benefits of security measures. And an organization gave us 60,000 data points, and I'm going to show you what we got out of that. We're going to call it Space Corp because we cannot tell you who that is. And now, how smart is smart enough? That's another thesis. The smart grid is super connected. At some point, you have to decide that there's enough connection, and Congress is very concerned about that. Okay, cyber attacks. Why we care? Because we have seen attacks on industry, Target, on infrastructure, in fact, the water production system of a town. Stuxnet, the attack on the Iranian uranium enrichment system. And the targets of interest for us are the enterprise network and the industrial control system. So I'm not talking about your computer at this point. So what are the elements of that cyber risk model? I put myself in the shoes of a CEO of a big company. That's what that's our target. It's the nature of that company. What information needs to be protected? What are the family jewels, and where are they? And by the way, many organizations do not know where they are, because they do not know sometimes the structure of their system. Who are the adversaries? Who are the bad guys that we are up against? We're going to talk about that in a minute. And we look at the probability of different scenarios and the consequences of successful attacks. So statistics tell us what has happened in the past, but we have to go beyond statistics to look at scenarios of how we could really lose our shirts. So who are the attackers? The script kiddies. So those, we call them the ankle biters. The nation states, here I'm showing you North Korea and when they attacked Sunni. Insiders, the worst, because we do not know who that could be, and it's all the people who have the information. Some of them shouldn't have it. The credit card skimmers, as you know, this has become a business, and the gray hat hackers, these guys who play on both sides of the equation. Okay, attacks and costs. I'm not going to read the whole list, but for example, website attacks, and we have seen yesterday that those could be pretty nasty. Lost or stolen devices. You would be amazed at how many of those Space Corp had experienced. Okay, what are the costs? Well, anything from the investigation cost, which is pretty routine. But if you lose your intellectual property and it's truly important to you, then you're in trouble. So these are the kinds of costs that we have tried to estimate, and I hope we've done it, with the help of statistics and expert opinions. What are the countermeasures? Again, a whole list, but let's start with firewalls. But I would say the 2 most effective that we have seen in the case of Space Corp were the full disk encryption and 2-factor authentication. Now, I know that a password with 16 characters that cannot be your birth date followed by your grandmother's are sometimes difficult to remember. Nonetheless, it turns out to work. Okay, the effectiveness depends on all kinds of things. The nature of your system, the type of attack, and the sophistication of your attackers. As we know, there are foreign countries that try non-stop as a full-time job. That makes it a bit tougher. So first, the empirical analysis of the data we had. On this axis, what I show over 6 years is all the incidents that we had, small dots when they were not too serious, big dots when they were really more serious for Space Corps. And what's important on this graph, this is the cumulative graph of the attacks that we had and the losses that were incurred. But what's important is first, the rate of attacks is relatively constant, contrary to what I had heard, and that in fact, after full disk encryption, they didn't have any big attacks. So it worked for them so far. Now, here is the mathematical challenge, is that we have a zone of small losses, and this, again, is the probability of exceeding different levels of losses. In a zone where we have statistics, fine, easy. There is a zone of very large things that have not happened yet. There we have to do another kind of analysis with scenarios based on statistics for parts of the scenarios and expert opinions for the rest. And we have an overlap zone that we have to fill, and we do some kind of mathematical scaling to be able to connect the two. And that's the only way we can get the whole story. Okay, these is to show you that we can quantify with these curves, again, the probability or the chances of exceeding different kinds of losses because of different kinds of attacks. So here is what you can see is that we have analytical results for each of the types of attacks. The difficulty is to look at what's happening in the upper bound, the worst case, and there we need, of course, expert opinions. But the yellow line that I've shown here is the probability of exceeding $1 million loss by each of the types of attacks that we had. And again, that came out of the work of Marshall Kuipers. Now, what you can see here is that the losses from the website compromise are usually small, but can get very, very big. And that we may not have in our statistics, and we need to look more carefully at the mechanism. Here, we looked at the effectiveness of training people in not responding to phishing. I'm sure all of you have pressed a button that you shouldn't press and opened a website that you shouldn't open. I have, I'm sure. And what we looked at is the training. And so the blue curve shows you what happens when 20% of the people actually push the wrong button. The red curve, when you have trained them to reduce that to 10%, to 15%, excuse me, and the green line, where you give enough training so that half the people who would have responded otherwise don't. And you see that there is quite a big difference in the chances of exceeding high costs. So, very beneficial. So what are the takeaways? That first, quantification can be done, which is important because the insurance and reinsurance companies are very interested in this work, and we have had to go to Switzerland to discuss all that. The rate of attacks in that organization was relatively constant, contrary to a lot of the perceptions. And finally, some countermeasures effectiveness could be assessed. And I would say, again, full disk encryption and two-factor authentication proved, in this case, to be very useful. And now for the second thesis I wanted to talk about, the smart grid cybersecurity. There was an attack in the Ukraine in December 2015 against 2 power plants, and what the attackers did was very simple. They took control of the mouse that controlled the system, and they targeted the production system. Okay, so was there too much connectivity? And there was a proposed US legislation in Congress to ask the companies to remove some of these connections. So how smart is smart enough? Well, the smart grids have a lot of benefits, and I'm going to show you what they are. But every time you add a connectivity, you add an endpoint, a door if you wish, through which the information can be removed. So smartness indeed is very good because it automates things that people would do by hand. You can detect problems much earlier, generally vegetation. You can integrate the solar and wind energy more easily. And also you can be much more efficient in terms of market and demand. Problem is that you have a flip side to that, which is cyber risk. I'm going to show you 3 examples: Aurora, the Phantom Mouse, and Countdown to Zero Day, which was Stuxnet. So what happened? Aurora was done by Idaho National Lab. It was a simulation of cyber attack. Unfortunately, things went wrong, and the information went public, so it was embarrassing. The Phantom Mouse, it was a software designed to take control of the mouse in a control center, and what the attackers had to do was simply to get into this Ukrainian power system and disconnect the substations one after the other. Stuxnet was even more interesting. It was against the Iranian enrichment system. Unfortunately, again, it spread accidentally beyond the intended target because there was a programming error. So that was a very big problem. Now, how do we do the analysis? We have 2 networks. We have a physical networks of things that are in your distribution system, but we have an information network above that with connections now through smartness. And as you can see, every single one of these information nodes can be an entry point into that system. So what Matt Smith has done with me is to do network model to look at the decisions that had to be made. And the operators indeed choose to connect in a subset of the nodes and create an overlaid smart grid information network over the physical network. And of course, as I said, every new node is a potential cyber attack vector. So we looked for the optimum connectivity, and we tried to balance, compute actually, the benefits, the price and customer demand data so that we knew how good it was for the consumer, but the risks also, and we have focused on the risk and failure scenarios that we could inform with experts and with data that we had from NESCOR, the North American Electric Sector Cybersecurity Organization. Okay, and what Matt did was to plot the benefits and the risk, benefits the upper curve, the risk the lower curve, the result in between, and he found that sure enough, there was an optimum level of connectivity beyond which the risks were higher than the benefits. So what are the takeaways of all this, of Matt's thesis? First, that the smartness of the grid is beneficial up to the point. After that, smarter means dumber. And what I mean by that is that the benefits are less than the risk cost. And that we can find that optimum. That's the most important. And the first task is to really understand what the story is. Really understand your system, really understand the cascading effect. Because if you lose something in Washington State connected to Oregon, connected to California, you're in trouble. Okay, so my conclusions is that I've seen the cyber risk being described as nuclear kind of stuff. I mean, it has been often apocalyptic, and it may be. But I would like to know what the story is and what we do next, and in what order, more importantly. Okay, so there's a lot of research regarding the possibility and the legality of various countermeasures. But we're not supposed to defend ourselves by destroying the servers that has attacked us. However, that's beginning to emerge as an option. But there is very little actual risk analysis done in that field, and that's what we have tried to do to guide better decisions. So a few years ago, I was told that cyber risk analysis was impossible, and now the question is, how can we do it better? And the question asked in that sense, again, by insurance, reinsurance, large corporation. So I think we are onto something, and we intend to continue.